this lesson, we're going to be talking about multiple representations of ratios. It's going to really sum up a lot of the things we've done already. Let's get started. Exploratory challenge. At the end of this morning's news segment, the local television station highlighted area pets that need to be adopted. The station posted a specific website on the screen for viewers to find more information on the pets shown and the adoption process. The station producer checked the website 2 hours after the end of the broadcast and saw that the website had 24 views. 1 hour after that, the website had 36 views. Okay, so the first thing we want to do is to create a table, it says, of how many views the website probably had 1 hour after the end of the broadcast based on how many views it had after 2 and 3 hours, which is the information they gave us. Use this relationship to predict how many views the website will have after 4, 5, and 6 hours after the broadcast. Okay, so let's go ahead and start making a table. The independent variable here is time. Time is usually an independent variable. We can't really control time. It moves in one path. We would need a time machine to affect time, make it a dependent variable. Okay, so time and viewers. So they didn't tell us 1, but I'm going to leave room for it. They told us 2. After 2 hours, there were 24 views, and after 3 hours, there were 36. So we can see that both of these have the same ratio. 2 to 24 and 3 to 36 is a ratio of 12 viewers per 1 hour. So we could extend this table. 4 would be 48, 5 would be 60, and 6 would be 72. Now we have a table that shows the answer for all those different hours, 1 through 6. So let's think about what is the constant C. We kind of talked about it in our process of solving the table above. So C in this case, we could take any of our values. We could take 24 over 2. We could take 36 over 3. Any of them are all going to turn out to be 12 over 1, or in other words, 12 viewers per hour. 12 viewers per hour. Okay, so using an equation to represent the relationship between viewers V, they gave us a variable, and number of hours H. So remember, we talked about C is going to be an important factor in our equations. So since we really want an equation that's primarily for the dependent variable, solved for the dependent variable, V, the dependent variable, is equal to 12H. So that's probably most likely the equation that is going to be helpful to you. But H equals 1 over 12V is a mathematically equivalent relationship, but I would say we would prefer this one. So it says use the table created in exercise 10 to identify sets of ordered pairs that can be graphed. We kind of breezed over ordered pairs earlier, but this is no more difficult than just putting the values in the table into an x, y parenthesis with a comma between them. So this is the format, x, comma, y. So if we look at the table of values, we have 1, comma, 12. We have 2, comma, 24. We have 3, 36. 4, 48. 5, 60. And 6, 72. So that's another way of representing it. So look right here in this first sheet on page 72. We have ordered pairs. We have an equation. We have the constant C, the ratio unit rate, and we have a table. Let's keep it going. Let's look at taking those ordered pairs that we had, and let's turn them into a graph. So another representation, another way we can display this data. Okay, so as we've already kind of talked about, time in hours is our independent variable, and viewers is our dependent variable. So I'm going to go ahead, I'm going to skip some room so I have enough, so I kind of stretch my data out. I'm going to count 1, 2, I'm skipping 3 lines every time, 3, 4, 5, and 6. And up here, I'm going to actually count by 3s, which makes every third line, or 4s, which makes every third line 12. So 12, 24, 36, 48, 60, and 72. Okay, let's not forget to put a title, y versus x. So viewers versus time. So let's throw the points in here. 1 with 12, 2 with 24, 3 with 36, 4 with 48, 5 with 60, trying not to go cross-eyed, that looks off, yep, 1, 2, too high. There we go. 6 with 72. Great. Okay, yours will probably be better. I'm going to do my best to draw a straight line here through all these points. It's always hard on my tablet here. Great, and we could keep going. I'm going to put an arrow on the end to say that this could keep going. We can figure out how many viewers we would expect after 7, 8, 9, 100 hours. Okay, that's all for page 73. Turning to page 74. It says, predict how many views the website will have after 12 hours. Use at least 2 representations, and it gives us some examples. Tape diagrams, we haven't done those in a while. A table, a double number line. So let's go ahead and show a couple of these other examples. Let's go and do a tape diagram. Tape diagram. So if we thought about our ratio, we have a ratio of time to viewers. Well, we know from earlier that our ratio was 1 to 12, or 12 to 1. So 1 hour goes with 12 viewers. So try to make this as best I can. So I'm going to break this up into 11 lines. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's our ratio of a 1 to 12. So I've got 1 box to 12 boxes. So if we want to figure out after 12 hours, 12 is going to be each box. So without having to put 12 in every single box, we know that there's 12 boxes. So 12 boxes times 12 in each box gives us 144 viewers. Great. Let's talk about this double number line that they're talking about. So double number line, a number line, counts up in order, might count by a different scale. So we're going to make 2 number lines, hence double number line. And so here's a number line for time, and here's a number line for viewers. The thing about them is that we're going to link them together. So each mark on the time is going to have a mark on the viewers. It might be a different number, but they're going to have a mark together. So if there's 0 time, there are 0 viewers. If there is 1 hour, there are 12 viewers. If there is 2 hours, there are 24 viewers. And we keep going. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so way out here, 12 hours, we know we're counting by 12 every time. Again, we'd get 144 viewers, matches up with 12 hours. So that's another representation. Okay, let's last show a table. We'd already started a table. We didn't take it all the way out to 12 hours. So time and viewers. Okay, so 1, 12, 2, 24, 3 with 36, 4 with 48, 5 with 60, 6 with 72, 7 with 84, 8 with 96, 9 with 108, 10 with 120, 11 with 132, and 12 with 144. So we have 3 representations here. We've got a graph here, that's a 4th representation. We've got ordered pairs, a 5th representation. Equations, 6th representation. We've got the unit rate, the scale factor, how many up to 6? 7 representations. All kinds of ways that we can represent this information differently. Okay, exercise 6 here is a different problem. So let's go through this one as well, just to see it in a different context. So exercise 6 says, also on the news broadcast, a chef from a local Italian restaurant demonstrated how he makes fresh pasta daily for his restaurant. The recipe for his pasta is below. You can read the recipe. It says, determine the ratio of the number of tablespoons of water to the number of eggs. So I'm going to go find water. Okay, tablespoons of water to the number of eggs. So in that order, it is 2 to 3. All right, so let's take this information and let's throw it into this table here. So we have 2 tablespoons of water. We're going to have 3 eggs. Of course, that's our ratio from above. So if it doubles, we're going to have 6. Tripled would be 9. Quadrupled would be 12. Times 5 would be 15. And times 6 would give us 18. It says to also show these as ordered pairs. That's what we're talking about with these x, y coordinates here. 2, 3. I'm going to kind of match them up here. 4, 6. 6, 9, 8, 12, 10, 15, and 12, 18. Great. Well, we have some graph space over here that we can also show it in a graph. So a little bit tough to squeeze it in here, but we're going to put the tablespoons of water down here. Tablespoons of water. That's our x value. This one doesn't really play to having an extremely clear independent dependent, but since the table was tablespoons of water, then number of eggs, that's going to be our x and our y. And our y value, as I said, is number of eggs. So our title is going to be number of eggs versus tablespoons of water. Great. I'm going to actually, it's not a very high number that we have to reach, so I'm going to be able to count by ones. I'm going to skip spaces and mark every 2 on the y-axis here, but I'm really still counting by ones. $16 and $18. We do have room actually for 20 up there. Okay, and the same thing on the x data. Don't have to go up too high. I am counting by ones, but I'm skipping spaces and marking every 2s. Just will make my writing a little easier to read. Still hard down there. Sorry for the limited space. 18 and 20. Okay, so the first ordered pair we have is 2, 3. 2 on the x, 3 on the y, right there. Then we have 4 with 6, and then we have 6 up with 9, 8 with 12, 10 with 15, making sure I'm not losing my place, 10 with 15, and 12 with 18. Great. We can go ahead and connect this with a nice line. Hopefully you use a ruler and yours will be a little straighter than mine. Good. So now we already have 4 representations. We've got the ratio up there, a table, ordered pairs, and a graph. Wonderful. It says, what would you have to do in order to find out how many eggs would be needed if the recipe called for 16 tablespoons of water? So 16 tablespoons of water, we'd have to extend our graph. So we'd have to extend the line. So if I'd gone by a bigger scale rather, we could have really seen this. But if we extended the line out here further and we followed up from the 16 on the x-axis, which is our tablespoons of water, we would have found a nice place where they meet. And I'm sure you guys can follow along that point would have been 24 eggs. So we would have gotten the point 1624, a little bit above the graph space that we have, but 1624 would have been that. So it says how many eggs would it have called for? 24 eggs. Great. All right, so exercise 7 is just saying determine how many tablespoons of water will be needed if the chef is making a large batch of pasta and the recipe calls increases to 36 eggs. Support your reasoning with at least 1 diagram. So we're going to show a couple different diagrams here again. So let's do tape diagram. So remember, we know that the ratio is 2 to 3, and that is water to eggs. So 2 tablespoons of water to 3 eggs. So if we want to get to 36 eggs, well, remember from our tape diagrams at the beginning, this is 36. So each of these boxes will be 12, same for the water. So that would lead us to 24 tablespoons of water. Great. All right, so let's look at another representation. Let's look at the double number line. So here, again, we're going to have water, and we're going to have eggs. All right, so 0 water is 0 eggs for both of them. If we have 2 water, we'll have 3 eggs, and we have to keep this going. 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. If we kept our numbering going all the way out, 24 eggs here would 24 tablespoons of water would correspond with 36 eggs. And we could do the same thing with a table. So our table, if we have water and eggs, if we have 2, it would have 3. If we have 4, we'd have 6. 6 and 9, 8 and 12, 10 and 15, 12 and 18, 14 and 21, 16 and 24, 18 and 27, 20 goes with 30, 22 goes with 33, and finally 24 tablespoons of water, 36 eggs. So there are so many different ways we can represent the data that we find in a ratio. We've got tape diagrams, tables, double number lines, equations, graphs, ordered pairs. So all of these different ways are different ways that we can convey the information to the people we might need to inform about the situation.